A bowl is formed by attaching 4 regular hexagons of side 1 to a square of side 1. The edges of the adjacent hexagons coincide as shown in the figure. What is the area of the octagon obtained by joining the top 8 vertices of the 4 hexagons situated on the rim of the bowl? This diagram that I just inserted hopefully will help you understand this question. So what they're looking at is this yellow part. That's what they want the area of, and that's an octagon. Now what I'll do is I'll draw the octagon, but I will draw it sort of like a square first. So this is, let's say, that square, and then that yellow part that they have highlighted is basically the octagon. So if I were to chop off these parts like that, these little triangles, and what remains is the octagon. So just like how they have drawn it in yellow, I'll draw it in yellow. So that is the shape that they want the area of. Okay, so let's see if we can work with this. Let's label this first. We are given some dimensions. We know that that is 1 based on the question. But this dimension we don't know, so I'll call that x. And this is 1, and similarly that'll be x, x, 1, x, x, 1, x, and x. Okay, so the area of this octagon is pretty straightforward. It would basically be the area of the square, which is x plus 1 plus x, all squared, minus these 4 rectangles. And each of those 4 rectangles would have an area of 1/2 base times height, with the base being x and the height being x. Okay, so this is the area. Now the problem is we don't know x. If we have x, then of course we can figure this out. So what I will do is look at this figure right here and draw something that hopefully will help. And I'm just going to draw this one line like this, like that. And that one line that I drew is parallel to this line right here. And because of that, I hope you are convinced that the distance from here to here will be the same as the distance from there to there. Now that distance we know is 1 because of the question tells us so, and therefore that distance up there is 1. Now what does this distance represent? It represents x. So that is how we come to the conclusion that x is equal to 1. Now we just have to sub 1 into here. So if we do, this will become 3 squared, I believe, right? 1 plus 1 plus 1 is 3. And this becomes 1 squared. Sorry, it will become 2 times 1 squared, so that's 2. So this is 9 minus 2, which is 7. And there you go. 7 is the answer. That would be B. Suppose that 13 cards numbered 1 through 13 are arranged in a row. The task is to pick them up numerically increasing order, working repeatedly from left to right. In the example below, cards 1, 2, 3 are picked up on the first pass, 4 and 5 on the second pass, 6 on the third pass, 7, 8, 9, 10 on the fourth pass, 11, 12, 13 on the fifth pass. For how many of the 13 factorial possible orderings of the cards will the 13 cards be picked up in exactly 2 passes? Okay, so let's talk about this before we jump right in. What do they mean by this 2 passes? Well, I'll give you an example. Let's say we have 1, 2, 3, and then 4, 5, and 6, like that. So what we're doing, I'm just giving you a small example. So what we're doing is we're going to pick up the cards, working from left to right in numerical order. So let's do the first pass. So the first pass, as we go through, we're going to pick up the 1, the 2, and the 3. So the 1, the 2, and the 3. And then what is left, we pick up in the second pass in numerical order. And in this case, it's 4, 5, and 6. And there we go. We picked up all the cards, and we did it in 2 passes. Now, the example they give here, they actually had to go through, I think, something like 5 passes. So the first pass, they pick up the 1, the 2, and the 3. And then they have to go through a second pass. And the second pass, they pick up the 4, the 5. And then the third pass, they pick up a 6. The fourth pass, they pick up the 7, the 8, the 9, the 10. And then finally, the fifth pass, they pick up the 11, the 12, the 13. So that's why it's 5 passes. So what they're saying is, if you take these numbers 1 to 13, of all the arrangements, which is 13 factorial, different arrangements, how many of those arrangements can you pick up these cards in just 2 passes? Okay, so hopefully that makes you understand the question. So let's work through with this. Now, let's say I have an example. Let's say I have the first 5 cards that I pick up in the first pass. So those numbers 1 through 5 are picked up in the first pass. Then, of course, the remaining numbers, which are 6 to 13, will be picked up in the second pass. Okay, this is just an example. So that means that in this case, my first pass ended with the 5, right? So I'm going to let that be sort of the important number that I'm going to use, and I'm going to illustrate it. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? Now the 1 through 5, we can put them in any order. So this first pass, we can put the 1 through 5 anywhere in here. So we have from 13 possible choices, we can choose 5. So this is the number of ways of putting those cards 1 through 5 along this 13 string pattern. So there's 13 choose 5 ways to place those 5 cards. So let's just choose one. Let's one way of doing it. Let's put the the 1 here, the 2 here, the 3 here, the 4 here, and the 5 here. Okay, this is just one of the 13 choose 5 ways. Now we get to the second pass. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now we've already put the 1 here, the 2 here, 3, 4, and 5. Now, how do we put the other numbers 6 to 13? There's only one way of doing that. If you want only 2 passes, second pass, they have to be put in numerical order. So that means that the 6 goes here, 7, 8, 9, 10, 11, 12, 13. So there's only one way of doing that. Got it? So that, I hope that makes sense. Now, here's the thing. You have to subtract 1 for this scenario, as it would give 1 pass. For example, you notice how up here I put the 1 here and the 2 here and 3 here and 4 here and 5 here, right? Well, one of the many ways of putting those first 5 is to put them in the first 5, like that. And then 6 through 7 would go here. Now that is a problem because this only involves 1 pass. If you pick up the cards, you could do it all in 1 pass. So this one has to be eliminated from our total number. You got it? So similarly, for all values of k, it would be 13 choose k up here. Okay, and then you'd have just one way of doing it down there, and then you have to subtract this scenario, because this scenario would give you 1 pass. All right, so let's do that. And also, you have to remember that you are only looking at values of k between 1 and 12. Because if k equals 13, then you would only get 1 pass. You would only basically get, you would get this scenario. So that's another thing we have to figure out or take into consideration. So for each value, for each k value, the number of ways is 13 choose k from up here. This is just 1, so that's not going to make a difference. You can put it in if you want, but you don't need to. And then subtract this 1 over here because we don't want that one. So essentially it becomes a summation type of scenario where k is going from 1 to 12, and you're calculating 13 choose k minus 1 for each of those. And I think most of you are pretty familiar with summation notation. So this would basically be 13 choose k for k equals 1 through 12, and then this will be a minus 12. We can put that out there. And then it just becomes 13 choose 1 plus 13 choose 2 plus 13 choose 3 plus ... You guys get the point, all the way till 13 choose 12. And then don't forget that minus 12. And then these numbers, I crunched them out. 1378, 286, 715, 1287, 1716, 1716 again, 1287, 715, 286, 78, 13, and then don't forget that minus 12. And when you calculate this, it's 8178. And 8178 is choice D for this question number 22. Problem number 23. Isosceles trapezoid ABCD has parallel sides AD and BC with BC less than AD, AB equals CD. There is a point P in the plane such that PA is 1, PB is 2, PC is 3, PD is 4. What is BC over AD? Okay, so let's first draw a diagram. And let's see what we can show on a coordinate grid. So I'm going to put this isosceles triangle on a coordinate grid, or isosceles trapezoid, I should say, and try to illustrate how we can work with this question. And let me label it. So we have A, B, C, and D. And then for each of these, I will give it coordinates. So A, I will call x1, y1, like that. And then B will be, B is x2, y2. C will have the same y coordinate, but it'll have a different x coordinate. And then D will have the same y coordinate as A, but it will definitely have a different x coordinate. So I think that's the labeling. And I've got to stick my, somewhere in there I've got to put in the P, right? So I'm not really sure where. I'll just put the P here. And this will be P. And then of course I've got to join those like that. And they tell me that those numbers are, what are they? P to A is 1, PB is 2, PC is 3, and PD is 4. Okay. All right, so pretty decent diagram, not drawn exactly to scale, but it's okay. And we eventually want to figure out BC over AD, okay? So there's lots of ways of doing this question. The system I like the best is to draw circles with a P being the center. And if P is the center, then that will definitely help. And the key in this question is to draw the P where the origin is. And I think that was what I should have done initially, but that's okay. I can do it now. So that's really important, actually. Okay, so now let's draw the circles. Now, B is a point on the circle. So if we were to draw a circle where P is the center and B is a point, the circle would look something like this, like that. Now I'm not gonna draw the whole circle in because it would make it confusing. And then same thing with A, it would make the circle look something like this. There would be a circle kind of like that. And then similarly, there'd be a circle kind of like this, and then a circle like that with D. Okay, so let's draw the equations now. For the circle with radius 1, it would be x1 squared plus y1 squared is equal to 1 squared. And that's equation 1. For the circle with radius 2, very similarly, it would be x2 squared plus y2 squared is equal to 2 squared. And the circle with radius 3 is x3 squared plus y2 squared is equal to 3 squared. And finally, the circle with radius 4 is x4 squared plus y1 squared is equal to 4 squared. And that's equation 4. All right, now one more thing is that since this is an isosceles trapezoid, if we were to take the midpoints of BC and AD, they would be the same. So if this is approximately the midpoint right here, and we took the midpoint of AD, they would essentially have the same x-coordinate. So midpoint formula, you can easily do x4 plus x1 divided by 2. That's going to give you this guy right here. And then that's going to be the same as this one, which is calculated with x3 plus x2 over 2, like that. So then you just get rid of the 2's, and therefore x4 plus x1 is equal to x3 plus x2. And this can be our equation 5, which hopefully we'll use later on. Okay, so now let's work with this. Let's look at these equations. The first one I want to use is equation 3, and from that I'll subtract equation 2. When I do, I get x3 squared minus x2 squared is equal to 5. And then I'll take equation 4 and subtract from it equation 1. And when I do that, I get x4 squared minus x1 squared is equal to 15. All right, so I think we're getting here somewhere, at least. And then we'll divide these two equations. So x3 squared minus x2 squared over x4 squared minus x1 squared is equal to 5 over 15. And let's factor this now. So x3 minus x2, x3 plus x2, all over x4 minus x1 times x4 plus x1, and that is equal to 1 over 3. And then let's see here, we can make this substitution now. x3 plus x2 is actually equal to x4 plus x1. So this part stays the same, but this x3 plus x2, I can put x4 plus x1. And that will help us because it'll allow us to cancel stuff out like this. So the good news is now that this cancels with this, and all you're left with is x3 minus x2 over x4 minus x1. And that is 1/3. Now, x3 minus x2, I'll write it up here. x3 minus x2 over x4 minus x1 is equal to 1 over 3. Now, go back to the diagram. x3 minus x2 is actually the distance from B to C. And x4 minus x1 is the distance from A to D. And in a very interesting way, we got exactly what they wanted. They wanted us to figure out BC over AD, and that's what we got. We got 1/3. So there you go. The answer to this is B. How many strings of length 5 formed from the digits 0 through 4 are there such that for each j element of 1 to 4, at least j of the digits are less than j? For example, 0, 2, 2, 1, 4 satisfies the condition because it contains at least one digit less than 1, at least 2 digits less than 2, at least 3 digits less than 3, and at least 4 digits less than 4. The string 2, 3, 4, 0, 4 does not satisfy the condition because it does not contain at least 2 digits less than 2. All right, so this is a example of a long question, and let's go through this. So first, before I jump right into it, let's talk about their examples. 0, 2, 2, 4, right? Sorry, 0, 2, 2, 1, 4. So we need it at least one digit less than 1. And we have that. We have a 0. So that is what we have. Then we need at least 2 digits less than 2. Do we have that? Yes, we have a 0 and we have a 1. Got it? Okay, then we keep going here. We need at least 3 digits less than 3. And we have that. We have actually 4 of them. So we just need at least 3. So we satisfied that. And then we need at least 4 digits less than 4. And do we have that? We have, so 0, 1, 2, and 2. So that is basically why this satisfies the condition of the question. So what they're asking for is how many are there? So that's going to be painful. So let's go through with this. Let's start off with a string that has only 1 digit, meaning all of them have to have 5 digits, but what I'm saying is that there's only one type of digit. And the only case that fits this is when they're all zeros. So that my 1 digit in this case is a 0. And this is the only one that satisfies this type of criteria where you have at least 1 digit less than 1, at least 2 digits less than 2, at least 3 digits less than 3, and at least 4 digits less than 4. So we have one case here. Then the next is when you have a string that has 2 different digits. So 2 different digits. And we have, for example, 0001, 0002, 00003, 00004. And then, of course, we can use 00011, 00022, 00033. And then 00111, 00222, and 01111. These are the only ones that will work. But here's the thing. There's several combinations for each of these guys. For this one here, these guys, for each one, from the 5 possible 1, 2, 3, 4, 5, there's 4 spaces to put those zeros. You got it? So that's how many combinations for each of these. And there's 4 of them. There's 1, 2, 3, 4. So we have to multiply by 4. And this is 20. Similarly, for these guys, from the 5 spaces, we have to choose 3. 1, 2, 3, 4, 5 spaces. But then we have to choose 3 for the zeros. And then there's 3 of those guys. 1, 2, 3. So we have to multiply this by 3. And this gives me 30. For these guys, it's going to be 5, choose 2, but there's 2 of them, so multiply by 2, that's 20. And this one is just 5, choose 1, and that's 5. And then so when you add up these, you get 75. So in a very similar way, you just got to keep going like this. And this is basically the table. And that table will give you the full. This is now the scenario when you have 3 different digits, and this is the scenario when you have 4 different digits, and then finally if they have 5 different digits down here, and each of these has a certain number. So if you recall the first scenario when there was only 1 digit, we only got 1 case. When there was 2 different digits, we got 75. When there's 3 different digits, they are saying there's 500. When there's 4 different digits, it's 600, looks like. And then when there's 5 different digits, you have 120. And when you add up all of these, you get 1296. So it's a very time-consuming question. I don't know how anybody could do this in a few minutes on a math contest. And 1296 is E for this one. Problem 25. Let R, S, and T be squares that have vertices at lattice points. Points whose coordinates are integers in the coordinate plane, together with their interiors. The bottom edge of each square is on the x-axis. The left edge of R and the right edge of S are on the y-axis, and R contains 9 over 4 as many lattice points as does S. The top two vertices of T are in R union S, and T contains 1/4 of the lattice points contained in R union S. The fraction of lattice points in S that are in S intersection T is 27 times the fraction of lattice points in R that are in R intersection T. What is the minimum possible value of the edge of length of R plus the edge length of S plus the edge length of T? All right, so we're going to need a lot of space, so we will make a little table here. We first need to make a comparison of the squares, and then we have the side length, and then of course we have the number of lattice points, All right, so the squares are the big one, and then S, and then T. And the side lengths, we'll just keep it simple. We'll just call it R, S, and T, lowercase. And then the lattice points are R plus 1 squared, S plus 1 squared, and T plus 1 squared. Now, if you're not sure why, I'll just illustrate it. Let's say you had a square, right? And it's a 5 by 5 square. And this is sitting on the axis like this. Well, you have this point, 0, 1, 2, 3, 4, 5, right? So notice we have 1, 2, 3, 4, 5, 6 actually lattice points, because you got to include that 0. And similarly up on the top, it would be 0, 1, 2, 3, 4, 5. So it would be 6 lattice points. That's why it's 6 times 6. And that's why we have to add that 1 there. So hopefully that makes sense. Okay, so now that we've got that figured out, that we've got this S plus 1 or R plus 1 all squared to figure out the number of lattice points, now let's proceed with the question. Now, entirely from the question up here, I'm going to actually try to use just the top, this part. I'm actually not going to use that part of the question. Just this part. They told me that we have a comparison, that the number of lattice points in the union of R union S is 9 over 4. Sorry, right here. Yeah, the left edge of R and the right edge of S, and then they tell us that R contains 9 over 4 as many lattice points as S. Okay. So that means that R has R plus 1 squared lattice points, and it's 9 over 4 as many lattice points as S. So that'll be S plus 1 all squared. So that's directly from the question. And then they tell me the other one, which is the 1/4 part of the question, that T contains 1/4 of the lattice points contained in R union S. So the number of lattice points in T would be T plus 1 squared. And that is 1/4. 1/4 of what, though? Not R or S, R union S. So all the lattice points in R and in S. So R union S. Okay. Well, the R union S basically is the number of lattice points in R, which is R plus 1, plus the number of lattice points in S, which is S plus 1. Now we have to subtract what's common. And the common lattice points to R and S would be the guys here, that on that line, the border between R and S. And that's basically going to be S plus 1. It's just the lattice points along those, along that y-axis, basically. So that's basically the other equation. So there we go. We got two equations, and we need to solve them. So here we go. This one and this one, down this guy. These are the two equations. Okay, so the first one, if we take the square root of both sides, we get R plus 1 is equal to 3 over 2 S plus 1. So that's a pretty easy one to solve. And when we solve this, we get R is equal to 3S over 2 plus a half. The second one, okay, that's going to take a little bit more algebra, unfortunately. So let's work with that one. So this next one is a little bit of a monster, so let's work with this one here, this guy. So we got t plus 1 all squared is equal to a quarter times r plus 1 times plus s plus 1 minus s plus 1, and there we go. All right, so let's work with this now. So this is going to be a quarter. I'm going to try to make a substitution here. This r plus 1 here is this guy right here. So instead of putting that r plus 1 squared, I'm going to put 3 over 2 3 over 2. Or I can just be a bit, I guess, direct and just put this guy here. R plus 1 squared is just that that same as up there, which is basically this 9 over 4 s plus 1 squared. Okay, so that'll be good because then we just have one variable, at least on one side. Okay, so let's move forward with that. So now we have this. So let's expand now. So we have 1/4, and this is going to be, this is like 1, so 4 over 4, 13 over 4. Yeah, 13 over 4. And then this s plus 1 squared is just going to be s squared plus 2s plus 1. And then, of course, don't forget about that minus s minus 1, or just take it out of the brackets. Okay. All right, so let's expand that. So that's going to be 13 over 4 s squared. And then that's going to be 26 over 4. And then minus that s is going to be 22 over 4. Yeah. And then we got 13 over 4 minus 1. So it'll be 9 over 4. Okay, great. And I think that's about as far as we can get. We can, of course, multiply through by that 1/4. So therefore, t plus 1 would be 13s squared plus 22s plus 9. And then in the denominator, I will have a 16. And then if I take the square root of both sides, this will basically be the root of 13s squared plus 22s plus 9. And let's see here. Let's just put everything. It'll be root 16. And then that's t plus 1. And then I guess at the end, we just have to subtract 1 from both sides, or 1 from the other side. Plus 9 over 16. All under the root sign. Minus 1. Okay. All right, great. Okay, so we got t. So we got t in terms of s. We have r in terms of s, right? They're not very pretty, but they're okay. Now, what is it that they want in our question? They want, if you go back to the question, basically, what is the minimum possible value for the edge lengths of r, s, and t? So what they really want is for us to figure out what is r plus s plus t. That's basically what they want. So r we have in terms of s. We have 3s plus 1 over 2. S is just s. And then we have this big long monster for t, which is 13s squared plus 22s plus 9 over 16, all square root, and then minus 1. Okay. So now what we're going to do is we're going to approximate, because the answer choices are very similar. If you notice the answer choices, they're very similar. They range by 1 each. So we want to approximate, so we will do so. This basically, when I simplify this a little bit, it becomes 3s plus 1 over 2 plus s. And then this part here I'm going to factor. So I'm going to put the 1/4 out front, and then it's going to be 13s plus 9. and then s plus 1. I believe that's the how it works. Yeah, 13s squared is 13. Yeah, that's how it works. Okay, so now we're going to approximate. That's why I put that little approximation symbol right here, that dot. This 3s plus 2, 3s plus 1 over 2 plus s, that when you simplify it, it actually becomes, this part and this part becomes exactly 5s over 2 minus a half. And then this part, I'm going to chop off the 9 and the 1. So I'm just going to approximate it as 13s times s square root like that. Because I'm just trying to get this to what it, sort of an approximate value. So this now becomes 2.5s minus 0.5. And then this one would be root 13s. Yeah, a quarter times root 13s. And then this is going to be 2.5s minus 0.5, and this is approximately 3.6 root 13 over 4. And this is about 3.4s minus 0.5, and we can approximate that as 3.4s. Okay, so what was the point of that? Well, our answer choices, if you look at the answers, they range between 336 and 340. Okay, so this 3.4s represents the sum of r plus s plus t. That's basically our answer. So 3.4s has to be equal to one of those approximately. We don't know which one. Is it 336? Is it 337? 338? 339? Or 340? Now I don't know. But let's say if it was 340, that means that s is approximately equal to 100. Okay. Now we also know that r, s, and t are all integers. Okay? And t is this big long song and dance up here. This one. So that was what? 13s squared plus 22s plus 9 all over 16, all root minus 1. Now, as before, I will I'm going to factor this to make it a little bit easier. So this basically is 13s plus 9, and it was s plus 1. And then don't forget that minus 1, and don't forget that 16. Okay, so for t to be an integer, this whole expression must be a perfect square. If t is an integer, then this guy must be a perfect square that is also divisible by 16. So it must be a perfect square that is divisible by 16. Okay? And with some trial and error, you hopefully can arrive that the only value of s that works is 99. Because when you put 99 in there, you'll get 13 times 99 plus 9 times 99 plus 1 over 16, all root minus 1. And this basically will be 1296 times 100 over 16 minus 1. And that is going to be 36 times 10 over 4 minus 1. And that is, let's see here, 90 minus 1, which is, of course, 89. So that is something that works. We got, when s is 99, we got t is equal to 89. And then when you plug it back into any of those formulas, like this one right here, with the very beginning, that r is 3s over 2 plus a half, we get r is equal to 3 times s over 2 plus a half, we get r is equal to 149. So therefore, finally, our r plus s plus t is 149 plus 99 plus 89, and that comes up to 337. So with a little bit of trial and error and a little bit of approximation, without even using the second part of the question, we got 337, and that would be choice B.